Hi everyone, this is Sandeep Sharma as Electronics.
And today we will be discussing about a very important topic in digital electronic design, which is clock domain crossing, CDC. Let me give you a brief overview of what we'll be looking at in this entire video. Please pay attention as most of these topics are asked in internship interviews and placement interviews, like metastability synchronizers, MTBF, or FIFO techniques, especially FIFO techniques. So make sure you learn as much as you can. So what is clock domain crossing? In digital electronic design, a clock domain crossing, or simply CDC, is a traversal of a signal in a synchronous digital circuit from one clock domain into another. Because of speed of light delays, timing skews, latencies, and some other problems, the size of a clock domain in such a synchronous system is inversely proportional to the frequency of the clock. In early computers, typically all the digital logic ran in a single clock domain. At first, each CPU chip ran in its own single clock domain, and the rest of the digital logic of the computer ran in another slower clock domain. But nowadays, in modern times, almost all the chips have different clock domains in them. And these different clock domains have clocks which have a different frequency, a different phase, or maybe both, due to either different clock latencies or different sources. Either way, the relationship between the clock in the two domains cannot be relied upon. So what happens when a signal traverses from clock domain 1 to clock domain 2? It may or may not be correctly sampled into the second clock domain. As the relationship between the two clocks is not defined very accurately, so we are never sure what data is read into the clock domain 2. A signal passing from such a crossing can go into metastability. Metastability refers to signals that do not assume stable 0 or 1 states for some duration of the time at some point during normal operation of the design. In a multi-clock design, metastability cannot be avoided, but its detrimental effects of metastability can be neutralized. A metastable output that traverses additional logic in the receiving clock domain can cause illegal signal values to be propagated throughout the rest of the design. Since the CDC signal can fluctuate for some period of time, the input logic in the receiving clock domain might recognize the logic level of the fluctuating signal to be different values, and hence propagate erroneous signals into the receiving clock domain. In this figure, clock 1 in the clock domain 1 launches a signal data 2 into clock domain 2, which is sampled by the clock 2 in clock domain 2 when it is falling from high to low, which leads to the signal being incorrectly sampled into the combination logic after this flop, and we say that it has gone into a metastable state. Can we ensure that this doesn't happen? Or at least can we make sure that this happens less or the probability is reduced? One way is by using synchronizers. A synchronizer is a digital circuit that converts a signal from a different clock domain into the recipient clock domain so that it can be captured without any metastability failure. Or in other words, we can say that a synchronizer is a device that samples an asynchronous signal and outputs a version of the signal that has transitions synchronized to a local or sample clock. The simplest and the most common synchronizer used by digital designers is a two flip-flop synchronizer. The first flip-flop samples the asynchronous input signal into the new clock domain and waits for a full clock cycle to permit any metastability on stage 1 output signal to decay. Then, the stage 1 signal is sampled by the same clock into the second stage flip-flop, with the intended goal that the stage 2 signal is now a stable and valid signal synchronized and ready for distribution within the new clock domain. For some very high-speed designs, the designers use a third flip-flop also, which increases the probability of capturing the right data to a satisfactory value. We can always reduce the probability to a much lower value by introducing more synchronizers, but they're just not very often required. Even after using synchronizers, we cannot be very sure whether the signal will be correctly sampled into the clock domain 2 or not. So how do we determine that whether a signal is correctly sampled or not? How do we predict that? The answer is mean time before failure, MTBF. It gives us information on how a particular event will fail It gives the average time interval between those two successive failures. Failure in this sense means a signal that is passed to a synchronizing flip-flop goes metastable on the first stage synchronizer flip-flop and continues to be metastable one cycle later when it is sampled into the second stage synchronizer flip-flop. Since the signal did not settle to a known value after one clock cycle, the signal could still be metastable when sampled and passed to the receiving clock domain, causing potential failure in the corresponding logic of that domain. Larger MTBF numbers indicate longer periods of time between potential failures, while smaller MTBF numbers indicate that metastability could happen frequently, causing failures within the design. Two of the most important factors that directly impact the MTBF of a synchronizer circuit are the sample clock frequency, that is how fast a signal is being sampled into the receiving clock domain, and the data change frequency, which is how fast is the data changing that crosses the CDC boundary. Shown here is the MTBF formula. Now there are some other factors which also affect MTBF, which are shown collectively as X. From this equation, it can be seen that failures occur more frequently in higher speed designs when sample data changes more frequently. Let's have a look at the signals which are passed from clock domain 1 to clock domain 2 without synchronization. The combinational output from the sending clock domain could experience combinational settling at the CDC boundary. This combinational settling effectively increases the data change frequency and potentially creating small bursts of oscillating data and thereby increasing the number of edges that could be sampled while changing, with a corresponding increase in the potential for sampling changing data and generating metastable signals. Signals in the sending clock domain should therefore be synchronized before being passed to a CDC boundary. The synchronization of signals from the sending clock domain reduces the number of edges that can be sampled in the receiving clock domain, effectively reducing the data change frequency in the MTBF equation and hence increasing the time between calculated failures. As evident from the diagram, the clock 1 logic settles and sets up on the A data flip-flop before being passed into the clock 2 domain. The A data flip-flop filters out the combinational settling on the flip-flop input A and passes a clean signal to the clock 2 logic. There can be two scenarios: if the sending clock domain has higher frequency than the receiving clock domain, or vice versa. Now we do need synchronizers in both of them, but the case where fast signals are sampled into the slow clock domain requires special attention. The signals which are passed from slow to fast clock domain can be sampled more than once and then be corrected by some combination logic. Consider the severely flawed condition where the sending clock domain has a higher frequency than the receiving clock frequency and that a CDC pulse is only one cycle wide in the sending clock domain. If the CDC signal is only pulsed for one fast clock cycle, the CDC signal could go high and low between the rising edges of a slower clock and not be captured into the slower clock domain. Now also consider the somewhat non-intuitive and flawed condition where the sending clock domain sends a pulse to the receiving clock domain that is slightly wider than the period of the receiving clock frequency. Under most conditions, the signal will be sampled and passed, but there is a small but real chance that the CDC pulse will change too close to the two rising clock edges of the receiving clock domain and thereby violate the setup time on the first clock edge and violate the hold time of the second clock edge and not form the anticipated pulse. In both scenarios, we need some special method so that the signal can be correctly sampled into the second domain. There can be two general approaches to the problem. We can have either an open loop solution to ensure that signals are captured without acknowledgement, or a closed loop solution that requires acknowledgement of receipt of the signal that crosses a CDC boundary. Let's have a look at them one by one. Let's study about open loop solution first. One potential solution to the problem is that to assert CDC signals for a period of time that exceeds the cycle time of the sampling clock. The minimum pulse rate should be 1.5 times the period of the receiving clock frequency. The assumption is that the CDC signal will be sampled at least once and possibly twice by the receiver clock. Open loop sampling can be used when relative clock frequencies are fixed and properly analyzed, and we know for sure what is the relation between A clock and B clock. The advantage of this method is that the open loop solution is the fastest way to pass signals across CDC boundaries that does not require acknowledgement of the received signals. But then it also has a disadvantage that the largest potential problem related to an open loop solution is that another engineer might mistake the solution for a general purpose solution, or the design requirements might change and an engineer might fail to reanalyze the original open loop solution. The closed loop solution is a more general solution and can be used in a variety of designs in contrast to open loop solution. In closed loop solution, we send an enabling control signal, synchronize it into the new clock domain, and then pass the synchronized signal back through another synchronizer to the sending clock domain as acknowledged signal. Now, the advantage in this method is that synchronizing a feedback signal is a very safe technique to acknowledge that the first control signal was recognized and sampled into the new clock domain. But then there is a potentially considerable delay associated with synchronizing control signals in both directions before allowing the control signal to change. What if we want to pass multi-bit signals between clock domains? When passing multiple signals between clock domains, simple synchronizers do not guarantee safe delivery of data. The problem is that multiple signals that are synchronized to one clock will experience small data changing skews that can occasionally be sampled on different rising clock edges in the second clock domain. Even if we could perfectly control and match the trace lengths of the multiple signals, differences in rise and fall times as well as process variations across a die could introduce enough skew to cause sampling failures on otherwise carefully matched traces. Therefore, multi-bit CDC strategies must be employed to avoid skewed sampling of the multi-bit value. The multi-bit CDC strategies include multi-bit signal consolidation, in which wherever possible we consolidate the multiple CDC bits into one CDC signal, and the multi-cycle path formulation, in which we use a synchronized load signal to safely pass multiple CDC bits. And the third one is to pass CDC bits using gray codes. We will be discussing about the first two. Multi-bit signal consolidation can be used in the case of two simultaneously required control signals. A register in the receiving clock domain requires both a load signal and an enable signal in order to load a data value into the register. If both the load and enable signals are driven on the same sending clock edge, there is a chance that a small skew between the control signals could cause the two signals to be synchronized into different clock cycles within the receiving clock domain. Under these conditions, the data would not be loaded into the register. As shown in the diagram, two signals B-load and B-enable are launched from the B clock domain with some small skew between them. The A clock domain captures the signal AQ2 load and AQ2 enable after synchronization with one clock cycle difference between them, because of which A data is missed to be sampled into the clock domain 2. The solution to the problem is simple. Consolidate the control signals together. Drive both the load and the enable register input signals in the receiving clock domain from just one load enable signal. Consolidation will remove the potential of two control signals arriving shifted in time and therefore solving our problem. The A data being received into the clock domain 2 is sampled and loaded into A bus. Multi-bit consolidation techniques can also be used in case of two phase-shifted sequential control signals. In the diagram, consider two enable signals AEN1 and AEN2 sequentially driven from a sending clock domain into the receiving clock domain to control the enable inputs of pipeline data registers. The problem with this setup is that in the first clock domain, the AEN1 control signal might terminate slightly before the AEN2 control signal is generated, and the rising edge of the receiving clock might occur in the slight gap between the two control signal pulses, causing a one-cycle gap to form in the enable control signal chain in the receiving clock signal. This would cause the A2 data value to be missed by the second register. The solution to this problem is quite simple. which is to send only one control signal just as before into the receiving clock domain and generate the second phase-shifted pipeline-enabled signal within the receiving clock domain. As shown in the diagram, only one control signal is received into clock domain 2, and then one phase-shifted pulse is generated through another flip-flop, and then that signal is given to the second register in the pipeline data registers. Now let us study about more robust techniques to pass multiple CDC signals across clock domain. Consider two encoded control signals which are being passed across clock domain. If the two encoded signals are slightly skewed when sampled, an erroneous decoded output could be generated for one clock period in the receiving clock domain. Some solutions to such problems are multi-cycle path formulations and FIFO techniques. There are at least two multi-cycle path formulations that can be used to fix the problem: closed-loop multi-cycle path formulation with feedback and closed-loop multi-cycle path formulation with acknowledged feedback. There are also at least two FIFO strategies that can act as closed-loop solutions to this problem: asynchronous FIFO implementation and two-dip FIFO implementation. In multi-cycle path, that is MCP formulation, we pass multiple CDC signals without synchronization, and simultaneously we pass a synchronized enable signal to the receiving clock domain. The receiving clock domain is not allowed to sample the multi-bit CDC signals until the synchronized enable passes through synchronization and then arrives at the receiving register. This strategy is called a multi-cycle path formulation due to the fact that the unsynchronized data word is passed directly to the receiving clock domain and held for multiple receiving clock cycles, allowing an enable signal to be synchronized and recognized into the receiving clock domain before permitting the unsynchronized data word to change. Because the unsynchronized data is passed and held stable for multiple clock cycles before being sampled, there is no danger that the sampled value will go metastable. Some advantages of this technique are that the sending clock domain is not required to calculate the appropriate pulse rate to send between clock domains. The sending clock domain is only required to toggle and enable into the receiving clock domain to indicate that the data has been passed and is ready to be loaded. The enable signal is not required to return to its initial logic level. Perhaps the most common method to pass a synchronized enable signal between clock domains is to employ a toggling enable signal that is passed to a synchronized pulse generator to indicate that the unsynchronized multi-cycle data word can be captured on the next receiving clock edge. A key feature of this synchronized enable pulse generation is that the polarity of the input signal does not matter. The D input is toggled high in cycle 1, and by cycle 4 a high signal has propagated the three synchronizing flip-flops. In cycle 3, the outputs of Q2 and Q3 flip-flops have a different polarity, causing the synchronized enable pulse to form on the output of the exclusive OR gate in the same cycle. Similarly, the D input is toggled low in the cycle 7, and by cycle 10 a high signal has propagated through the three synchronizing flip-flops. And again in cycle 9, the outputs of the Q2 and Q3 flip-flops have a different polarity, causing the synchronized enable pulse to form on the output of the exclusive OR gate. In addition to generating a pulse of any D input polarity, the synchronized enable pulse generation circuit also has a Q output that follows the D input delayed by 3 clock cycles. The Q output is frequently used as a feedback signal and passed as an acknowledged signal through another synchronized enable pulse generation circuit in the sending clock domain that we will see in the next subsequent slides. Let's have a closed loop MCP formulation with feedback technique. In this, we use MCP formulation to pass the enable signal back to the sending clock domain as an acknowledged signal. In the figure, the acknowledged feedback signal BACK generates an acknowledged pulse AACK that is used as an input to a small ready-busy one-state FSM block that generates a ready signal called AReady to indicate that it is now safe to change the data input ADataIn value again. Once the AReady signal goes high, the sender is free to send new data and the accompanying asend control signal. This is an automatic feedback path that assumes that the receiving clock domain will always be ready for the next word synchronized through an MCP formulation. The second technique is closed loop MCP formulation with acknowledged feedback. This technique uses an MCP formulation to pass the enable signal back to the sending clock domain as an acknowledged signal only after the receiving clock domain acknowledges the receipt of the data with a B load pulse. The receiving clock domain has a small wait-ready one-state FSM that sends a valid signal called B-valid to the receiving logic when data is valid on the input to the data register. The data is not actually loaded until the receiving logic acknowledges that the data should be loaded by asserting the B-load signal. There is no feedback to the sending clock domain until the data has been loaded. Then, the B-acknowledged signal is sent back, the same as MCP formulation with automatic feedback. This feedback path requires action on the part of the receiving clock domain before data is captured and feedback is sent. We finally come to the most important part of CDC, which is FIFO techniques. Questions on FIFO are asked in internship interviews as well as in placement interviews. So please pay utmost attention while listening to this part of video. FIFO is first in first out memory. These chips are used in buffering applications between devices that operate at different speed or in applications where data must be stored temporarily for further processing. Some FIFO memory reads with one clock and writes with another simultaneously. Synchronous operations require a clock. Flow control generates full and empty signals so that inputs do not overwrite the contents of the buffer. Depending on the device, FIFO memory can be unidirectional or bidirectional. FIFO memory can include parallel inputs and outputs as well as programmable flags. There are at least two interesting FIFO implementation strategies that can be used to address multi-bit CDC signal integrity, which are asynchronous FIFO implementation and 2-deep FIFO implementation. Let's discuss about multi-bit CDC signal passing using asynchronous FIFOs. An asynchronous FIFO is a shared memory or register buffer where data is inserted from the write clock domain and data is removed from the read clock domain. Since both sender and receiver operate with their own respective clocks, using a dual port buffer such as FIFO is a safe way to pass multi-bit values between clock domains. A standard asynchronous FIFO device allows multiple data or control words to be inserted as long as the FIFO is not full, and then extract multiple data or control words when convenient as long as FIFO is not empty. The write pointer always points to the next word to be written. Therefore, on reset, both pointers are set to 0, which also happens to be the next FIFO word location to be written. On a FIFO write operation, the memory location that is pointed to by the write pointer is written, and then the write pointer is incremented to point to the next location to be written. Similarly, the read pointer always points to the current FIFO word to be read. Again, on reset, both pointers are reset to 0. The FIFO is empty and the read pointer is pointing to invalid data because the FIFO is empty and the empty flag is asserted. As soon as the first data word is written to the FIFO, the write pointer increments, the empty flag is cleared, and the read pointer that is still addressing the contents of the first FIFO memory word immediately drives that first valid word onto the FIFO data output port to be read by the receiver logic. The fact that the read pointer is always pointing to the next FIFO word to be read means that the receiver logic does not have to use 2 clock periods to read the data word. If the receiver first had to increment the read pointer before reading a FIFO data word, the receiver would clock once to output the data word from the FIFO and a clock second time to capture the data word into the receiver. That would be needlessly inefficient. The FIFO is empty when the read and the write pointers are both equal. This condition happens when both pointers are reset to 0 during a reset operation, or when the read pointer catches up to the write pointer having read the last word from the FIFO. A FIFO is full when the pointers are again equal, that is, when the write pointer has wrapped around and caught up to the read pointer. This is a problem The FIFO is either empty or full when the pointers are equal. But which? Well, one design technique used to distinguish between full and empty is to add an extra bit to each pointer. When the right pointer increments past the final FIFO address, the right pointer will increment the unused MSB while setting the rest of the bits back to 0 as shown in figure, in which the FIFO has wrapped and toggled the pointer MSB. The same is done with the read pointer. If the MSBs of the two pointers are different, it means that the right pointer has wrapped one more time than the read pointer. If the MSBs of the two pointers are same, it means that both pointers have wrapped the same number of times. Using n-bit pointers where n-1 is the number of address bits required to access the entire FIFO memory buffer, the FIFO is empty when both pointers including the MSBs are equal, and the FIFO is full when both pointers except the MSBs are equal. One of the favorite questions of interviewers is regarding the FIFO buffer depth calculation. So let's study about that with an example. But before proceeding, we should have some things in mind. Like, data should not be continuous as otherwise FIFO will overflow and data will be lost. Then, data should be in the form of bursts. Burst is basically size of the data bits sent. There should be minimum burst to burst cap so that receiving clock domain gets sufficient time to read complete FIFO. Also, there can be one or more idle clock cycles between two successive reads and two successive writes. So, let the sending clock frequency Fa be 200 MHz and the receiving clock frequency be Fp 15 MHz. Let the burst size be 100 bytes and the idle cycles between successive reads is 1 and between successive writes is 2. Now, time taken to write 1 data byte will be 3, which is 2 plus 1 into the time period of sending clock cycle, which will be 15 nanosecond. Similarly, time taken to read 1 data byte will be 1 plus 1 into receiving clock time period, which will be 133.333 nanosecond. The time taken to write one burst will be 100 into 15, which is 1500 nanosecond, and the total number of bytes which will be read during the burst writing will be 11 bytes. We have to take the lower number if the answer is in decimal. Therefore, the buffer depth will be 100 minus 11, which is 89. Speaking in general, let's suppose the sending clock frequency is Fa, receiving clock frequency is Fp, and the burst size is P, with idle cycles between two reads as IR and between two writes as IW. The general formula for buffer depth can be written as shown in the slide. The second FIFO technique is multi-bit CDC signal passing using 1 tape or 2 register FIFO synchronizer. Since the FIFO is spelled using only 2 registers or a 2 deep dual port RAM, counters used to detect full and empty are simple toggle flip-flops, which is really nothing more than a 1-bit binary counter. On reset, both pointers are cleared and the FIFO is empty and hence FIFO is not full. We use the inverted not full condition to indicate that the FIFO is ready to receive a data or control word. That is, WRDY is high. After a data or control word is put into the FIFO using wput, the W pointer, which is WPTR, toggles and the FIFO becomes full. Or in other words, the W ready signal goes low, which also disables the ability to toggle the WPTR and therefore also disables the ability to put another word into the 2 register FIFO until the first word is removed from the FIFO by receiving clock domain logic. What is especially interesting about this design is that the WPTR is now pointing to the second location in the 2 register FIFO. So when the FIFO does again become ready, that is when WRDY is high, the WPTR is already pointing to the next location to write. The same concept is replicated on receiving side of the FIFO. When a data or control word is written into the FIFO becomes not empty. We use the inverted not empty condition to indicate that the FIFO has a data or control word that is ready to be received. that is RRDY read ready is high. By using two registers to store the multi-bit CDC values, we are able to remove one clock cycle from the send MCP formulation and another cycle from the acknowledge feedback path. I hope you liked the video and understood most of it. I will be posting more such videos, so please subscribe and press the bell icon, and do comment about the video and what other videos do you want me to make. You can also follow me on Instagram for regular updates. Thank you.